Greetings everyone. In today's lecture, we shall look at what we call the solution of Euler's equation for the shortest distance problems. For that case, we shall consider 2 points 1 and 2 on a given surface, but we understand that geometrically we can obtain the shortest distance between any two given points by using what we call the straight lines. Now, for that case, let us consider the curve y equaling to f of x. And when we use the definition of the arc length for the Cartesian equation, we shall be able to come up with the solution of Euler's equation for the shortest distance problems. Let us come into that. By definition, the arc length is defined by the integral from 1 to 2 of the square root of 1 plus dy dx. This one here squared, then times dx. By definition, we define the arc length as that. Now, from here we can obtain s as the integral from 1 to 2 of the square root of 1 plus. I want to denote this one with y dash, which is squared, then times dx, where our y dash is simply representing dy dx. Now from here we can say that this will imply that our ds will simply be, when you differentiate on both sides, you will be able to obtain the square root of 1 plus y dash, which is squared, then times dx. Now, from there, since we want to use the Euler's differential equation, let us consider, we shall consider our f. Let us consider our f to be the square root of 1 plus y dash, which is squared. So we are considering this one here to be our function, because we understand that Euler's equation, you need to have a function f. Having got our function f, we understand that Euler's differential equation is given by del f del y del f del y minus d dx of del f del y dash equaling to 0. We proved this in our last lecture. So for those who are just watching this lecture, make sure that you watch our first lecture to be able to understand where we got this one from. Now for that case, we shall call this one equation 1, and from this equation it demands us to get del f del y first and del f del y dash. So let's get del f del y from this given equation star. What is del f del y? You realize that from this given equation there is no y, meaning that when I take del f del y, it will simply be 0. Now let us look at del f del y dash, because this equation 1 demands us to get del f del y dash and del f del y. Having got our function f, we understand that Euler's differential equation is given by del f del y minus d dx of del f del y dash equaling to 0. We proved this in our last lecture. So for those who are just watching this lecture, make sure that you watch our first lecture to be able to understand where we got this one from. Now for that case, we shall call this one equation 1, and from this equation it demands us to get del f del y first and del f del y dash. So let's get del f del y from this given equation star. From equation star, from star, what is del f del y? You realize that from this given equation there is no y, meaning that when I take del f del y it will simply be 0. Now let us look at del f del y dash, because this equation 1 demands us to get del f del y dash and del f del y. Now, from our equation star, which is f equaling to the square root of 1 plus y dash, this one which is squared, we shall have to get del f del y dash. What will be del f del y dash? So we shall differentiate this. So this one will be same as having a half times, when you differentiate this one here, you'll get 2y dash divided by the square root of 1 plus y dash, which is squared. Simply, this will give us y dash over the square root of 1 plus y dash, which is squared. So that is what we shall get as our del f del y dash. Now, from equation 1, from equation 1, we can now substitute in del f del y minus d dx of del f del y dash, then equaling to 0. Let us substitute. We have del f del y, we have this one here. So on substitution, we shall be able to get 0 minus d dx, 0 minus d dx, 0 minus d dx times, so del f del y dash, we have got it as y dash over the square root of 1 plus y dash, which is squared. The whole of this one is equal to 0. So since this is 0, when you divide through by that, you will remain with d dx of y dash over the square root of 1 plus y dash, which is squared. And this one here is equal, to 0. So let us try to solve this equation here, and we obtain the solution. So this will imply d of y dash over the square root of 1 plus y dash, which is squared, will be equal to 0 dx. Integrate both sides, so integrating on both sides, we shall obtain y dash over the square root of 1 plus y dash, which is squared. And this one here will be equal to a, where our a will be a constant. So for that case, let us try to manipulate this equation here. Let us square both sides. So we shall say squaring on both sides, we shall be able to obtain y dash, which is squared, over 1 plus y dash, which is also squared. So this square root here will go with the square, this will be squared, and a will also be squared. So this will give us a squared. So from there, we can try to rearrange. This is y dash squared equaling to a squared into 1 plus y dash, which is squared. So this one here will be same as y dash, which is squared, equaling to a squared plus, we are opening the brackets, a squared, then y dash, which is also squared. So let us try to rearrange and make a y dash the subject. So we shall obtain y dash, which is squared, minus a squared times y dash, which is squared, and this one will be equal to a squared. So let us rearrange this. So there is a common factor here, which is y dash squared. So y dash squared into this will be 1 minus a squared, which is equal to a squared. So we want to make y dash the subject, so y dash a squared will simply be equal to a squared over 1 minus a squared. So having obtained that, let us take square root on both sides. So we shall obtain y dash, which is equal to a out of the square root of 1 minus a squared. So we have our y dash as a out of the square root of 1 minus a squared. So this one here is easier to solve. Y dash, remember it represents dy dx. So we have dy dx, which is equal to a over the square root of 1 minus a squared. So we can simply have this as, let us have a out of the square root of 1 minus a squared to be any given constant, for example m. So in other words, we shall have dy dx, which is equal to m. So dy dx is equal to m. In other words, we can say dy is same as m dx. So on integration, we shall obtain integrating on both sides, we shall obtain y, which is equal to mx plus a given constant of integration, which is, for example, c. Looking at this obtained solution, you realize this is a straight, which is a straight line. You realize this is a straight line. Equation. This is a straight line equation, and this equation here will be representing the shortest distance between the given points 1 and 2. So we can say y equal to mx plus c, which is a straight line equation that represents shortest distance between points 1 and 2. And this will be the solution of the Euler's equation for the shortest distance problems. Thank you for watching. We meet in the next lecture.
Yeah.